Good morning all. In this session, the relation between the phase to neutral voltage and line to line voltage in case of a three-phase balanced system of voltages and the relation between the phase current and the line current in case of balanced delta connected and star connected loads are discussed. A balanced load is one in which the phase impedances are equal in magnitude and in phase. And there are two possible configurations of three-phase loads. One is the delta connection and another is the star connection. Here in this figure you can see that three impedances ZA, ZB and ZC are connected in the form of a delta, and the points of connection are taken, or the terminals are taken out for connecting to the supply. And in case of a star connected system, you have three impedances Z1, Z2 and Z3 connected together, and the three terminals are taken out for connecting to the system. And in case of a star connected system, you have one more additional terminal which will be taken from the point of interconnections, or the common point of connection of the three impedances, which is not there in the delta connection. In case of a delta connected load, you have only three terminals which can be taken out and which can be connected to the system. But in case of a star connected system, it is possible to have four terminals A, B and C, and the third one which is taken from the common point of the impedances is termed as the neutral connection. And a system of load is said to be balanced if all the phase impedances are equal in magnitude and in phase. That means magnitude of ZB, ZC and ZA and the phases should also be same. So for a balanced delta connected load, ZA in complex form equal to ZB, ZC, all these are in complex form, and it should be equal to delta Z delta, where Z delta is the load impedance per phase. And in case of a star connected load, here also if it is said to be balanced, the Z1, Z2, Z3 should be equal, and which can be represented as Z star. And you can see that all these Z1, Z2 and Z3 Z1, Z2, Z3 and Z star are represented in phasor form. That means all these Z1, Z2, Z3 and Z star are complex quantities, where Z star is the load impedance per phase. Now let us see the relation between the phase to neutral voltages and the line to line voltages. Here in this figure you can see that three coils of a three-phase generator are connected in star. As we have seen from the basics of the three-phase generation, there will be three similar coils in a three-phase generator, and the magnitude of the voltages generated in all the coils will be same, and the voltages will be displaced by 120 degree each. That means if you are considering VAN, or the voltage of the A coil as reference, the voltage in the second coil or the B coil will be lagging with respect to the first voltage in the first coil by an angle of 120 degree. Similarly, the voltage in the third coil will be lagging with respect to the first coil by an angle of minus 240 degree, which is equal to plus 120 degree. So if you consider an ABC sequence whose voltages will be expressed as VAN equal to VP angle 0, VBN equal to VP angle minus 120 degree, and VCN is equal to VP angle plus 120 degree. And if the coils are connected in star as shown in this figure, here if you find the potential of the voltage of the line A with respect to B, similarly the voltage of the line B with respect to C, and the potential of voltage of the line C with respect to A, it can be calculated as shown here. That means the VAB, that is the potential of the line A with respect to B, or the voltage of the line A with respect to B, and it is represented in phasor form. And as a vector, you can represent VAB as VAN plus VNB, where N is a point between A and B if you are adding the vectors, or if you are calculating the vector VAB. VAB can be represented as VAB is equal to VAN plus VNB, and all these values VAB, VAN and VNB are vectors. And here you can see that as VNB is a vector, VNB can be written as minus VBN. That means VNB is equal to minus VBN. So VAB, line potential voltage of the line A with respect to B will be VAN plus VNB, which will be equal to VAN minus VBN. And if you substitute this expression for VAN and VBN, you get VAN minus VBN is equal to VP angle 0 minus VP angle minus 120 degree. This VP is the magnitude of the voltage of the phase to neutral, or the voltage of the magnitude of the voltage of each coil. So here VP can be taken out as a common factor, and inside the bracket you will get the cos 0 plus j sin 0, which will be 1 plus 1 itself, minus here you get the cos of minus 120 degree plus j cosine of minus 120 degree, which will be 1 minus 1 by 2 minus j root 3 by 2. You can use these relations. These relations can be used. 1 angle minus 120 degree will be equal to cos minus 120 degree plus j sin minus 120 degree, which will be equal to minus 1 by 2 minus j root 3 by 2. So if you substitute these relations here, you can simplify this as VP into, here you will get a 3 by 2 plus j root 3 by 2 will be there. So if you take root 3 as a common factor, it can be written as root 3 VP, and inside the bracket you get root 3 by 2 plus j 1 by 2, which can be written as root 3 by 2 plus j 1 by 2, which can be written as 1 angle 30 degree, because 1 angle 30 degree will be equal to, using this relation, it will be root 3 by 2 plus j 1 by 2. So by substituting that here, you get VAB is equal to root 3 VP, which is the magnitude angle 30 degree. That means if you consider this as the reference vector or the reference phasor, or if you consider VAN as the reference voltage, the line to line voltage VAB can be written as root 3 VP angle 30 degree, and from this relation you can see that magnitude wise the line to line voltage will be root 3 times the phase voltage, and it will be leading by an angle 30 degree with respect to the phase to neutral voltage of the A phase, or with the reference voltage. So the relation can be written as VL, the line voltage will be equal to root 3 VP in magnitude. That means magnitude of the line voltage will be root 3 times the phase voltage. Similarly, if you calculate VBC, it will be equal to VBN minus VCN, which will be equal to root 3 VP angle minus 90 degree. Similarly, if you follow the same step, you get VCA is equal to VCN minus VAN, which will be equal to root 3 VP angle minus 210 degrees. So you can use these relations also. By substituting these relations, you get these relations. VBC equal to root 3 VP angle minus 90 degree, VCA equal to root 3 VP angle minus 210 degrees. So from here you can see that if you consider these three relations, VAB, VBC and VCA, all magnitudes are equal to root 3 VP, and the angles are respectively 30 degree, minus 90 degree and minus 210 degrees. If you consider VP as the phase voltage and VL as the line voltage, all these magnitudes are same, and it is according to this relation. Line voltage will be equal to root 3 VP. Now if you represent these informations in phasor diagram, we get it as here. Here you can see that these are if you follow the ABC sequence, these are the phase voltages, VAN, VBN and VCN. Now if you add it vectorially, from the previous slide, we have calculated the line-to-line voltages analytically or mathematically. Here you can get the line-to-line voltage by vectorial or by the phasor sum of the respective components. VAB is equal to VAN plus VNB, and VNB can be written as minus VBN. Now, minus VBN will be, in this phasor diagram, you can see that this is VBN. So, minus VBN will be in this direction. That means the direction will be just opposite to that of VBN, but magnitude will be same. So if this is VBN, then this phasor will be VNB, or it will be minus VBN. So VAB can be written as VAN plus VNB. So if you find the vector sum of VAN and VNB, you get VAB. So VAB will be, and this magnitude we can calculate from this parallelogram. It will be root 3 times the magnitude of this. So VAB is root 3, magnitude wise it is root 3 times the phase voltage, and it is leading with respect to the reference vector by an angle 30 degree. Similarly, you can form other vectors. Here VAB is this. VAB is obtained by the vector sum of VAN and VBN reversed. Similarly, VBC will be obtained by the vector sum of VBN and VCN reversed. VCN is this and VCN reversed is this. So, if you find the vector sum of these two vectors, you get this. That is VBC. Similarly, VCA is obtained by the vector sum of VCN and VAN reversed. That means this is VAN and VAN is reversed here. If you find the vector sum of these two vectors or the phasor sum of these two phasors, you get the resultant as VCA. So, if you represent these phasor quantities in polar form, it will be VAB is equal to root 3 VPS. That means the magnitude of this vector you can calculate from this parallelogram. It will be root 3 times the magnitude of this phasor. So finally we get these relations. If the expression for the phase 2 neutral voltages are VPH angle 0, VPH angle minus 120 degree and VPH angle minus 240 degree, then the line voltages in this order. Say if we are following ABC sequence, VAB can be represented as root 3 VPH, that is the magnitude angle 30 degree. That is clear from here because the voltage VAB is leading with respect to VAN by 30 degree, and VBC is equal to root 3 VPH angle minus 90 degree. This is the reference direction, this is the voltage VBC. Similarly, VCA is equal to root 3 VPH angle minus 210 degrees. This is the direction of VAN and this is VCA, and you can see that this angle is equal to minus 210 degrees. That means it is in the in the clockwise direction, and this is the relation between the line voltages and the phase voltages. Now let us see what will be the relation between the line currents and the phase currents if you connect a load across this generator. And here in this figure you can see that a balanced 3-phase load which is connected in star is connected to the 3-phase supply. Here you can see that the coils of the generators are connected in star, and the neutral of the generator as well as the neutral point or the common point of the balanced 3-phase star connected load is also connected here. Now, if you are applying Kirchhoff's voltage law to these loads, here if you apply Kirchhoff's voltage law to this loop, here you can see that if you start from this point, you get the first term as VAN and you have no drop across this, and the drop across this is IA into ZY, and you are traveling in the direction of the current, so you are meeting a drop in potential. So with the sign convention, you get this equation. So if you start from this point, you have a voltage source here which is represented as VAN, that is plus VAN. Now you have a drop across this, that is minus IA into ZY. Both are phases, and now there is no drop across this. So if you apply Kirchhoff's voltage law to this loop, you get this equation VAN minus IA ZY equal to 0. Similarly, if you apply Kirchhoff's voltage law to this loop, if you start from this point, say here you get VB. If you start from this point and if you apply Kirchhoff's voltage law to this loop, starting from this point N, going via this and returning to this point, and if you apply Kirchhoff's voltage law to that loop, you get the equation VBN minus IBZY, which will be equal to 0. This VBN, IB and ZY all are in phasor form. Similarly, if you apply Kirchhoff's voltage law to this loop, starting from the point N, going through this and completed at N. So, the equation corresponding to that loop will be VCN minus ICY, all are in phasor form. And here, from N, this is equal to 0, and from here you get IA is equal to VAN divided by ZY. Both are in phasor form. Similarly, from this equation you get IB is equal to VBN divided by ZY. And VAN, if you represent it as VAN angle 0 degree, VBN can be represented as VAN angle minus 120 degree divided by the ZY. ZY is in complex form. and it will be equal to, if you represent the VAN by ZY as IA, the phasor IA, it will be, and magnitude wise, if you find the magnitude of VAN by ZY, it will be the same as VAN by ZY, because all these loads are same and it is a balanced load. So you have IA is equal to VAN by ZY. Similarly, here you have IB is equal to VBN by ZY, which is written as VBN can be written as VAN angle minus 120 degree divided by ZY. Now, if you find the magnitude of this, if it is represented as IA, it can be written as IA angle minus 120 degree. Similarly, IC is equal to VCN by ZY, and VCN can be written as VAN angle minus 240 degree, and ZY magnitude wise, if we are finding the ZY is the impedance, so VAN divided by minus 240, IC is equal to VCN by ZY, which is, and VCN is given by VAN angle minus 240 degree divided by the impedance, and it will be equal to IA angle minus 240 degree. It is to be noted that IA is a phasor quantity which is given by VAN by ZY. VAN is a phasor, ZY is a phasor. So, IA will be a vector. And if you consider this vector as reference, IB can be written as IA angle minus 120 degree. That means IB is lagging with respect to the phasor IA by an angle of minus 120 degree. Similarly, here you can see that IC given by VCN divided by ZY is equal to VAN by ZY, which is the phasor quantity IA here, and that IA angle minus 240 degree. That means this phasor IC is lagging with respect to this phasor by an angle of minus 240 degrees. And here you can see that IA is the magnitude. Here you can see that this is the line current, and you can see that the same current will be flowing through this impedance. Similarly, this IB is the line current in the second line, and it will be flowing through the impedance ZY. That means the phase current or the current in the B phase is the same as the line current IB. Similarly, here IC is the line current in the C line, and which is the current flowing through the impedance in the third line or in the C line. That means here the phase current is the same as the line current, but there is a phase difference between it. And here you can see that in the star connected system, the line current is the same as the phase current, which can be seen from these relations. Now, if you add, here you can see that if you consider IA, IB and IC, they form three vectors which are separated by an angle of 120 degree each. That means IB lags with respect to IA by an angle of 120 degree, and IC lags with respect to A by an angle of minus 240 degree. Now, if you add this up, IA angle 0 plus IA angle minus 120 degree plus IA angle minus 240 degree, you will get it as 0. That we have seen from the basic relation between the balanced three-phase voltages. And here you can see that if you add IA plus IB plus IC, or if you add IA, IB and IC together, you will be getting it as 0. That means if you apply Kirchhoff's current law to at this point, you can see that IA is coming to the node, IB is coming to the node, and IC is coming to the node, and IN is also coming to the node. So if you write it as IA, and as if you apply this relation and apply Kirchhoff's current law to this loop, if you apply Kirchhoff's current law to this loop, you get IN plus IA plus IB plus IC is equal to 0. And we have already a relation IA plus IB plus IC is equal to 0. That means IN is equal to minus of IA plus IB plus IC, which will be equal to 0. That means the current from this neutral of the generator, current from the neutral of the generator to the common point of the star connected load is 0. That means these 2 points, small n and capital N, are at the same potential, and this point is at a potential of 0. So this point will also be at the same potential as that of, because all these voltages are measured with respect to n. So Vn will be equal to 0. That is why there is no current flowing between these 2 points when it is connected by a solid line. So the neutral line can thus be removed without affecting the system. That means there is no current through the a line connecting the neutral of the generator and the neutral of the load. In long distance power transmission, conductors in multiples of 3 are used, with the earth itself acting as the neutral conductor. Practically, you might have seen the transmission line, which has only 3 lines A, B, C in a circuit, and the neutral will be, or the return point will be the earth itself.